Hold this question like a smooth stone in your hand. How long will the universe exist? Not just our world, not just our sun, but everything, the galaxies, the dark arcs between them, the bent light, the quiet space. How long does it all continue? It's a simple question that opens into a gentle vastness. Because the universe is not a machine with a clock we can wind down and read. It is more like a breath, expanding and thinning, a tide drawing out so slowly that each of us sees only one small wave. Start with what we can see. The night is dim, but it isn't black. Stars pour out their light, and between them, galaxies do the same, billions of small lanterns arranged into spirals and ovals. Their light has traveled for millions, even billions of years to reach you. That light carries whispers of the universe's youth. It tells us that the cosmos had a beginning, not in space, but of space, a hot, dense state that we call the Big Bang, more than 13 billion years ago. From that beginning, everything expanded. The fabric of space stretched. The first atoms formed, then the first stars, then galaxies. Then, eventually, you and me, and this quiet question at the edge of sleep. For a long time, we assumed expansion would slow under gravity's pull, like a ball thrown upward. It might slow forever, or reverse into a collapse, or balance perfectly. But the universe surprised us, the way quiet things often do. In the late 20th century, astronomers watching distant supernova noticed that those standard candles were dimmer than expected. Not because they were weak, but because the space between us had stretched faster than we imagined. The expansion of the universe was speeding up. Something dark energy was pushing the cosmos apart with a soft insistence. That small discovery changed the shape of our future. If the expansion accelerates, then distant galaxies will drift away faster and faster, until their light can never reach us. A horizon will form in space, like the line where sea meets sky, beyond which we can never see. In time, most of the cosmos will slip over that line, not because it vanishes, but because the river of space carries it too swiftly away. We will remain in a small island of gravity, our local group of galaxies, while the larger ocean grows calm and empty to our eyes. But how long? How long do stars keep burning? How long do black holes hold the night? How long does dark energy keep its steady push? These are the pulses we'll feel in the story to come. The universe has eras. The age of stars, the age of embers, the age of black holes, and then a quiet that isn't quite nothing, but is close. Each era has its numbers years, with so many zeros they stop feeling like years and begin to sound like wind. Before we float forward, listen to the pace. The sun is a middle-aged star. It has about 5 billion years of steady burning ahead. Red dwarfs, the small, faint stars, will glow not for billions, but for trillions of years, 10,000 times the current age of the universe. Even in that sentence, you can feel the scale softening the mind. Trillions, then quintillions, then times so long we borrow mathematical notation to keep them straight. The future is not an empty blank. It is detailed, layered, patient. What will shape that patience? Several gentle, stubborn facts. Gravity gathers matter into stars, and stars give light. Over time, gas is used up, star formation slows, planets cool, orbits change. On the largest scales, dark energy pulls the background further apart. Inside that background, black holes swallow what wanders too close. And then, this is one of the strangest promises of physics. They slowly evaporate, whispering their mass back into radiation over times longer than any star could ever know. The universe does not crash. It fades. There are other possibilities too. The accelerating expansion might not be constant forever. If it strengthens beyond a certain threshold, space itself could tear galaxies and atoms apart in a dramatic, big rip. That scenario seems unlikely given what we measure, but it is not forbidden. Or the vacuum of space, the quiet baseline of reality, might be like a ball perched in a shallow valley, waiting for a quantum nudge to roll into a deeper state. If that happens, a vacuum decay, the laws of physics could change in a wave racing at light speed, rewriting the universe in an instant. It's a delicate speculation, and the likely timescales dwarf any human concern. If it is possible, it is almost certainly very far away. But it reminds us, the future rests on physics we are still learning to hear. For now, the most measured, steady picture is this. The universe expands forever, gently accelerating, stars burn and die. Matter drifts and cools, black holes rule for a time, and then end. And the cosmos settles toward heat death, a state where energy is so evenly spread that nothing much can happen. No free gradients, no engines, no lights. Just a thin bath of low-energy quanta, and the almost silent hum of a horizon. If that sounds bleak, sit with it a moment, and notice another feeling behind it, a quiet awe. The fact that we can sketch any of this from a small planet under a thin sky is astonishing. We can hold a piece of the universe's calendar in our hands, not as prophecy, but as a soft map. We can follow matter from fire to stars, to dust, to black holes, to faint radiation, and in doing so, we can place our questions where they belong, inside a story that continues long after our candles go out. So, how long will the universe exist? As far as we can tell, indefinitely, but growing simpler, calmer, colder. It will not end with a bang we can schedule. It will end as music ends when the last vibration fades. The tune isn't over yet. In fact, in cosmic terms, it has barely begun. To understand the verses to come, we'll step back into the early science that revealed expansion, trace the clues that led to dark energy, and find our footing before we walk into the future. In a few breaths, we'll stand with those who first measured the sky's drift. We'll touch the faint afterglow of the Big Bang. We'll listen to the equations that let us count the eras. The universe is old. Its future is older. And somewhere in that distance, a soft answer waits. Imagine a clear, moonless night centuries ago. No electric lamps, no planes, no hum. The sky is a river of light, and humans tilt their faces upward with a question that has never left us. What is all of this, and how does it last? Early answers were stories, patterns woven into the stars themselves. Over time, our stories gained instruments, lenses, mirrors, prisms, and the sky began to speak in numbers. In the early 20th century, an astronomer named Henrietta Swan Leavitt noticed a rhythm in certain stars' Tiphide variables that brighten and dim like slow heartbeats. The pace of that heartbeat reveals their true brightness. Comparing that to how dim they appear tells us their distance. Leavitt gave us a yardstick. With it, we could measure the scale of the universe beyond a guess. Edwin Hubble used that yardstick to look at fuzzy spirals we thought might be clouds within our own galaxy. He found they were separate galaxies, distant islands of stars. When he split their light with a spectrograph, he saw a signature, a stretching of the light toward red, a redshift. The more distant the galaxy, the greater the redshift. Hubble plotted distance against redshift and saw a line, a law of expansion. Space itself was stretching, not stars flying apart through static space, but the fabric between them lengthening. While the telescopes listened to light, theorists wrote equations for a universe that could grow. The mathematician Alexander Friedmann, using Einstein's general relativity, found solutions where space expands or contracts. Georges Lemaitre, a priest and physicist, connected those solutions to the idea of a cosmic beginning, the primeval atom, the start of expansion. In the middle of the 20th century, Arno Penzias and Robert Wilson pointed a radio antenna at the sky and heard a faint hiss, a uniform whisper coming from every direction. It was not pigeons. It was the afterglow of the hot early universe, the cosmic microwave background, cooled by expansion to a gentle 3 degrees above absolute zero. The glow was a child's picture of the cosmos, steadfast and noisy with tiny ripples. Those ripples became galaxies. This was our foundation, an expanding universe from a hot, dense start, strewn with hydrogen and helium, cooling into stars and planets. The next step came later and more quietly. Astronomers studying type, supernova white dwarf stars that explode at a nearly standard brightness, used them as candles to measure the expansion history. The result was a curve that bent the wrong way. Instead of slowing down under gravity's pull, the expansion leaned toward acceleration. To fit the data, the universe needed something with negative pressure, a smooth energy that filled space and pushed things apart. We call it dark energy. The simplest form of dark energy is the cosmological constant, a term Einstein once put into his equations to keep the universe static and later called his greatest blunder. It turns out to be no blunder at all. A cosmological constant means that every cubic meter of space holds the same tiny, persistent energy. As space expands, there is more of it, so the total push grows. The effect is mild on human and even galactic scales, but over billions of years, it writes the long arc of the future. You might ask, what is this energy, really? We do not know in the satisfying way we know the mass of an apple. We can measure its strength. We can describe its effect. But its origin remains one of physics' soft puzzles. It may be a property of the vacuum itself, the lowest energy state of quantum fields. It may be something that evolves, slowly changing with time. For now, the best measurements say it behaves very much like a constant. And that is enough to draw a calm, careful sketch of tomorrow. Think of the universe in eras. After the Big Bang, radiation ruled. Light and high-energy particles carried most of the energy. As expansion cooled the cosmos, matter took over. Gravity gathered it into structures, and stars bloomed. We live in this matter era, but we are approaching the threshold where dark energy dominates. In truth, it already does. It accounts for most of the energy budget of the current universe. Its dominance means structures no longer grow on the largest scales. Galaxy clusters that are not already gravitationally bound will drift apart, receding beyond one another's reach. The cosmic web, once lively with growth, will enter a quiet middle age. Measurements of the cosmic microwave background by missions like WMAP and Planck, of galaxy clustering by large surveys, and of supernova by patient teams, all converge on this picture. The universe is about 13.8 billion years old. It is flat on large scales, or very nearly so. It contains ordinary matter, the atoms we know, and dark matter, which tugs with gravity but does not glow. And it contains dark energy, smooth and soft, steering the long-term expansion. To ask how long the universe will exist, we need more than expansion. We need to understand what happens to light and matter when the expansion is accelerated. There is a horizon in such a universe, a distance beyond which light emitted today will never reach us, no matter how long we wait. The number depends on the exact expansion rate and the behavior of dark energy, but think of it as tens of billions of light years. Beyond that horizon, objects are not lost. They continue, but their stories cannot arrive here. The universe divides itself into isolated chapters. Inside our chapter, gravity keeps some things together. The Milky Way and Andromeda are on course to meet and merge in roughly 4 to 5 billion years, forming a new, larger galaxy, sometimes nicknamed Mildromeda. Our local group, a cluster of a few dozen galaxies, is bound. It will remain an island in the accelerating sea. The rest of the cosmic archipelago will slip farther and fade. We also need to know the physics of small, patient processes fusion in stars, cooling in remnants, decay in particles, evaporation in black holes. These are the metronomes of the deep future. They tick far too slowly for us to hear, but we can read their marks in the lab and in the sky. The standard model of particle physics tells us how light and matter behave. General relativity tells us how space and time curve. Between them, and with a few delicate open questions, we can sketch the calendar. Set the hands of that calendar now. The next hundreds of millions to billions of years are dominated by familiar processes. Star birth and death, planetary orbits, galactic mergers. Beyond that, the outlines blur to a soft wash of times, so long they almost stop being time, but they do not stop. They carry us onward. At the edge of this part of our journey, you can feel a hinge. Past and present are the warm, bright rooms behind us. Ahead is a hallway lit by red dwarf stars, long-lived and calm. Beyond them, the light thins, and through the dimness, you can see the glint of black holes, waiting with patient gravity. In the next breath, we'll walk the hallway, stopping to touch the doors. The stellar era, the degenerate era, the black hole era, and the long quiet afterward. Begin with what we know best, stars. Our sun is a fairly typical star, and it will live, in total, about 10 billion years. Half of that remains. Red dwarfs, which are smaller and cooler, are the true elders of the cosmos. They burn their hydrogen fuel so sparingly that some may shine for up to 10 trillion years. If the universe were a city, red dwarfs would be the porch lights left on long after the street lamps go dark. In the near future in cosmic terms, our local story changes shape. 4 to 5 billion years from now, the Milky Way and Andromeda will merge. Their stars will mostly pass by each other. Galaxies are mostly empty space. But gas will crash into gas, and waves of star formation will be triggered. New suns will blaze for a time. The night sky of any future Earth-like world will be a tangle of star streams and arcs, a slow, elegant ballet. Meanwhile, the sun will exhaust the hydrogen in its core in about 5 billion years, swell into a red giant, and alter the inner solar system. Whether Earth is engulfed or left as a charred, airless rock is a fine detail determined by tides and winds and loss. Either way, our planet's days of seas and weather are finite. The sun will shed its outer layers, forming a planetary nebula, and leave behind a white dwarf, a hot ember the size of Earth, made mostly of carbon and oxygen, cooling for a very long time. Across the universe, this cycle repeats. Massive stars end more dramatically, exploding as supernova and leaving neutron stars or black holes. Smaller stars fade into white dwarfs. The stellar era, while it lasts, is fertile and busy. But star formation needs gas, and gas is used up and locked away in leftovers. Over the next 100 billion to a trillion years, starbirth slows to a trickle. The universe goes from a bright adolescence to a calmer adulthood. Imagine a sky lit mostly by red dwarfs and the occasional flare of a nova. Planets still circle these small suns. There may be eyes to see that light, and minds to think under it, but the stage is quieter. The energy budget of the universe is becoming parsimonious. Each star is a careful candle. Beyond a trillion years, many stars have died. White dwarfs cool and dim. Brown dwarfs objects too small to ignite fusion drift in the dark. Planets wander. Gravity continues its slow work, shuffling orbits. In multiple star systems, tiny tugs add up. Over time, many planets are flung into the interstellar medium. Some are captured, some collide. Stellar remnants gather in the centers of galaxies, where supermassive black holes hold court and the outlying stars drift on. There is an entire literature of patient possibilities here. Two brown dwarfs might collide and briefly fuse into a small star. White dwarfs, as they cool, crystallize. Their interiors become solid lattice of carbon and oxygen, diamonds the size of worlds, glowing faintly in the cold. In the deep future, a recent idea suggests that under extreme pressures and long timescales, nuclear reactions fusion, triggered by quantum tunneling in dense matter, could spark in the cores of the coldest white dwarfs, setting off a final, faint kind of supernova after time so vast that writing them requires towers of zeros. Whether that happens depends on physics we are still refining. It is a reminder that even in stillness, there are surprises. As ages pass, new energy sources dwindle. Cosmic rays still cut through space. Radioactive nuclei with very long half-lives continue to decay, but their heat is local and brief in the grand scheme. If protons are stable, if they do not decay, then matter can endure in principle indefinitely. If protons decay, as some grand unified theories suggest, then atoms themselves have a timer. Experiments have not seen proton decay, and they set lower limits on its half-life that are staggering, beyond 10 to the 34 years. If decay exists, it is slow beyond slow, a whisper, stretched across eons. If it does not, matter persists, though its metal is tested by gravity and entropy. This is the beginning of the degenerate era, where most luminous stars are gone, and the universe is filled with remnants. White dwarfs, neutron stars, brown dwarfs, black dwarfs, theoretical, fully cooled white dwarfs, and black holes. Galaxies have merged into quieter forms. Their outskirts are thin. The local group has long since coalesced into a single large elliptical galaxy, an island in a dark sea. Beyond its shores, the acceleration has carried everything else beyond casual contact. We live in this picture, in a provincial city with no neighboring towns. The highway is there, but it only runs away. Time continues. If protons decay, white dwarfs and neutron stars slowly crumble into lighter particles. If not, they remain inert and cold, their interiors calm. Gravity is not done. Encounters in star clusters and galactic cores continue, though each meeting is much rarer than before. Many objects are ejected into intergalactic space. Others fall toward the central black hole and vanish behind the event horizon, their mass added to the dark heart at the center. Black holes become the main actors. If you could see in the language of gravity alone, you would watch them dance and merge, absorbing the last dense knots of matter. Then they would begin to fade, very slowly, by a process known as Hawking radiation, a quantum effect in curved spacetime. The details are subtle, but the upshot is gentle. Black holes are not permanent. They leak. Consider the clock for that leak. A black hole the mass of our sun would take about 10 to the 67 years to evaporate one, followed by 67 zeros. A supermassive black hole, millions or billions of times heavier, would last incomparably longer, up to roughly 10 to the 100 years, depending on its mass. These numbers are not guesses. They grow from equations tested in many corners of physics. The last light in the universe, in many futures we can write, is the soft final flare of a black hole as it gives its mass back to the sky as heat. We stand here, at the edge of the black hole era, with a new horizon appearing. It is not only that black holes evaporate, it is also that the universe, under dark energy, develops an event horizon of its own, a cosmic boundary beyond which the rest of reality is permanently out of reach. That horizon has a temperature and almost inconceivably low warmth, and it radiates, just as black holes do, though far more faintly. In a sense, the universe itself, becomes a kind of quiet thermal room, with a single low heat left humming. What comes after the last black hole? A long, long night. But even in that night, there are questions worth asking. Is there truly an end, a last chapter? Or does time simply stretch until the line between moments blurs? At the close of this part, hold two images. A red dwarf star glowing in a gentle barn-red light with a planet skimming close to keep warm. And far beyond it, a massive black hole, silent but not immutable, fated to whisper itself away. Between those two images lies nearly all the future that includes light. Beyond them, we enter the age of shadows. Step softly. When the last ordinary star has faded, the universe enters its quietest posture. No new suns rise on their own. The free gas is mostly gone or locked into cold objects. Energy is no longer released in bright, sustained ways. What remains are processes that are glacial, statistical, rare, decay, evaporation, slow encounters. If protons decay, the degenerate era thins out more quickly. Atoms in the blackest of dwarfs would disintegrate, leaving behind leptons and photons, drifting through space. Neutron stars, held together by immense pressure, would resist longer, but even they would eventually surrender if decay is fundamental. If protons are stable, those remnants remain intact, and the universe is dotted with dark stones that never crumble, only cool. Black holes bind this darkness together where gravity is deepest. In the cores of ancient galaxies, by now merged into something smoother, supermassive black holes have eaten what they can. Smaller black holes have joined the feast. Gravitational radiation, faint ripples in spacetime, has carried away energy in mergers, tightening orbits until horizons touch. The sky, to any observer in these times, would be almost perfectly dark, perhaps with a handful of very cold, very faint objects, unless one looks in the language of gravity or remembers that horizons, too, are not forever. Hawking radiation is hard to picture. It is not steam venting from a hole. It is, instead, a property of the horizon itself, of the way quantum fields fill space, even in a vacuum. In a simple image, pairs of virtual particles can be separated by the horizon's tidal pull. One falls in, the other escapes, becoming real, taking a tiny bit of mass energy from the black hole in the process. Over immense time, that process balances the black hole's appetite with a patience that outlasts galaxies. As the black hole shrinks, it grows hotter, radiating more intensely, until at the last instant it flashes and is gone, leaving behind a cloud of low-energy particles and a faint signature of the energy it had stored. Timescales help us feel this. Imagine writing a 1 with 100 zeros after it. That's a googol. The lifetimes of the largest black holes can approach that span in years. 10 to the 100. Compare that to the universe's current age, 13.8 billion. A 1 with 10 zeros. The difference is like the difference between a heartbeat and the age of mountain ranges, magnified beyond comfort. In that comparison, the present is not even the beginning of the story. It is a footnote at the end of the prologue. Beyond the last evaporation, the universe becomes a thin sea of particles and very low energy radiation. dark energy still pushes. The event horizon still hums with a temperature so tiny that words fail, something like 10 to the minus 30 degrees above absolute zero. In such a de Sitter-like future, time itself feels different, not to the physics, which continues, but to our imagination. There are no more engines. Entropy is near its maximum. Free energy, usable energy that can drive change has been spent. This is heat death, the slow conclusion of a long meal. There are twists even here. In systems with horizons and finite entropy, there is a concept called Poincare recurrence. Given enough time, random fluctuations might, in theory, produce brief and local decreases in entropy, conjuring temporary structures out of the thermal bath. The times to wait for such events are not just long. They are beyond words, exponential of large numbers. But in a purely mathematical sense, they crack the door. Discussions of such recurrences spill into philosophical questions about observers and minds that spontaneously assemble Boltzmann brains, and whether a universe that lasts long enough would be dominated by such chance awarenesses rather than beings grown in stars. Most physicists file this under interesting but distant, a signpost to the limits of our models more than a guide to anyone's future. What about gentler alternatives? The big rip we mentioned, the scenario where dark energy's push strengthens over time, would end the universe's structures in a more dramatic way, tearing galaxies, solar systems, and eventually atoms apart as expansion overwhelms every force. Observations today suggest dark energy is stable, with an equation of state very close to -1, consistent with a cosmological constant. That makes the Big Rip unlikely, at least with what we know now. Vacuum decay, the possibility that our current vacuum is metastable lives in the space between particle physics and cosmology. The Higgs field, which gives particles mass, might be perched in a shallow well, not the absolute minimum. A quantum tunneling event could nudge it into a lower state, rewriting the masses and couplings of particles as the new vacuum expands at light speed. If that happened, nothing could outrun the wavefront. We would not see it coming. The best calculations, given the measured mass of the Higgs boson and the top quark, suggest that if metastability is real, the lifetime of our vacuum is staggeringly longer than the current age of the universe, perhaps by hundreds of orders of magnitude. This makes vacuum decay an intellectual horizon more than a practical forecast. It keeps us humble. It says, the ground under the universe is something we continue to study. Set those branches aside for a moment and return to the quiet standard picture. In that future, the geography of the cosmos simplifies. What once was a web becomes a set of isolated oases, and then a single oasis, and then only the gentle temperature at the horizon. If there is consciousness left anywhere, it would need to be extraordinarily patient, extraordinarily thrifty, feeding on scant gradients, storing information in ever more subtle ways. There are speculative papers that calculate how long computation could continue in such a universe, squeezing thought from stretched seconds, but their conclusions are often sobered by the relentless approach of heat death. The walls close in not by crushing, but by thinning. And yet, in the middle of this thinning, beauty remains. The equations that carry us here, Einstein's field equations, quantum field theory, thermodynamics, have a spare elegance. The way they fit together to tell such a vast story is a kind of art. We are not required to like the ending for it to be meaningful. The meaning comes partly from the fact that we can say anything coherent at all across such spans. So, how long will the universe exist? In this picture, forever, in the sense that time does not stop. But meaningful structure, the kind that shines and remembers, is time-limited. Stars end in about 10 trillion years. The remnants and black holes rule until something like 10 to the 100 years. After that, the night. A very long night. Let this not feel like loss. Let it feel like perspective. We live in the era of stars. We live when galaxies still speak to one another with light. Our instruments drink from the cosmic microwave background and taste the oldest afterglow. We are early enough that there is much to see, early enough that the sky is still rich. In the next and last part, we'll come closer again to the scale of our lives. We'll ask what this long forecast means for us emotionally and practically. We'll tuck ourselves into the universe's timeline like a bookmark, grateful for the page we're on, and then close the cover with a soft hand, knowing the story continues out of sight. Sit for a moment with the knowledge that you are alive in a bright window of time. Human history is a thin thread laid across a wide tapestry, and that tapestry is woven from stars. To ask how long the universe will exist is, in a way, to ask how to live knowing there is a dawn and a dusk we will never see. The answer can be gentle. It can be a kind of gratitude. On practical scales, the forecast shapes how we search and how we care. We search for life elsewhere because we recognize that stars are temporary lanterns, and we are curious companions. We build instruments to read the sky's old light while it is still available to us. In the distant future, galaxies will have slipped beyond our horizon, but today they are here, sending their messages. We study dark energy not only to polish equations, but to understand the stage we stand on. Every measurement, every map, every quiet night at a telescope is a way of pressing our hand to the universe's pulse. Caring arrives in the same breath. Knowing that stars and worlds change does not make our days small. It makes them vivid. It tells us that oceans and forests are rare arrangements of matter that took billions of years to learn the trick of being alive. It suggests that we might treat them with tenderness, as something the universe tried for a while, and that we were lucky to be part of. Our choices ripple on human timescales, not cosmic ones, but the backdrop reminds us that warmth is a temporary gift. It encourages us to keep it. There is also comfort here. The universe is not ending soon, not by any human measure. The sun has billions of years. A galaxy has the leisure to merge and reshape. If intelligence finds ways to stretch itself, it may have long spaces in which to thrive, to travel, to think. The silhouette of heat death does not forbid meaning. It invites creativity within the window we have. Think of a musician playing a piece that does not last forever. The finitude sharpens the notes. It's worth returning to the question that started us. How long will the universe exist? A calm answer, repeated softly, is indefinitely. With our best measurements, we expect the expansion to continue and accelerate, stars to fade in trillions of years, black holes to evaporate in time so long that counting them feels like a meditation. Along the way, there are contingencies we will continue to test. Is dark energy truly constant? Are protons stable? Is the vacuum as solid as it seems? Those questions are not sources of fear. They are trails in the woods, each leading to more sky. Emotionally, knowing the long future is knotted with shadow can be oddly luminous. It frees us from the pressure to make things eternal. It invites us to make them beautiful. It invites us to learn and to share, to turn the complicated science of gravity and quantum fields into stories that can be held at bedtime and carried into dreams. A timetable measured in googols can become a lullaby if we let it. The lullaby does not promise us forever. It promises us wonder for as long as we listen. Imagine at last a future observer, a being living near a red dwarf under a russet light, walking on a beach of long frozen sand. The sky is sparse. The constellations we know are gone. Maybe this being knows about us because we left signals, artifacts, inscriptions hewn in math. Maybe not. They look up and ask their own version of our question. How long will it last? The answer they receive will rhyme with ours. Long enough to love the time you are given. Long enough to learn and to rest. Then let your gaze return to now, to your breath, to the soft weight of the present. The universe's future unfolds at a pace that does not demand anything from you tonight. If your curiosity has been fed, if a small, quiet awe has settled, then we have walked well together. Thank you for being here, for leaning into the vastness with such a human heart. If you'd like to drift again through calm, curiosity-driven science, through shields and stars, through oceans and orbits, you are warmly welcome to subscribe and keep company with us. Sleep well, and may the long future feel like a gentle sky above your dreams.